Okay, test. Does that work? Cool. All right, thanks. And as the title suggests, this is a talk about type systems with union and intersection types. So let's quickly review what those are. Union types are simply the joins in your subtyping hierarchy. That is, a member of a union is a member of either type of any component of the union. And intersection types are the meets in your subtyping hierarchy. So any member of an intersection is a member of all the components of an intersection. And while these are rather old concepts, they have only recently started showing up in major programming languages. And one of them is the programming language Ceylon, whose developers wanted to use union and intersection types to model features like nullability and several others. So in Ceylon, the type hierarchy starts with top, and then there are two special types called null and object, which are disjoint, and everything else is a subtype of object. So in contrast to Java, where the null value is a value of every type, here null is only a value of this null type. And in order to get nullable types of anything else, you need to union them with this null type. How might you use that? Well, you might have a list of nullable strings. But eventually, you would want a list of just strings without all those nulls in there. And you want the type checker to support the reasoning about that. So there should be a filter nulls function that takes a list of nullable things and returns the list without those nulls. What might the signature of such a function look like? It turns out the best way of writing this function is this one, which is you have a generic type parameter t, you take a list of arbitrary t's that may or may not be nullable, and in the return type, you intersect this t with object, filtering out the null value again from the potential types in that list. So now, syntactically, the type of that filter nulls returns is this list of nullable strings intersected with object. And in order to type check our assignment, we need to make sure that this is a subtype of a list of strings. So how do we reason about that? Well, unions and intersections are distributive. So this is really a list that looks like this. And now we have this intersection of null and object, which are disjoint, which means they have no common instances. So really that is equivalent to the bottom type. And then there are a few more steps that are simply unioning with empty sets and intersecting with subtypes. But eventually we'll get that this is in fact equivalent to a list of string, which we wanted. This is great, but sadly it's only an intuition for why this should work. So far, when we started our work, there wasn't an algorithm for Ceylon that could have implemented this. In particularly, disjointness and distributivity are properties that are really hard to reason about. The only line of work that could reason about disjointness and distributivity is called semantic subtyping, but the techniques of that line of work don't scale to generics and so weren't applicable to Ceylon. So this is where our framework comes in. In our framework, which is also implemented as a Coq library you can use for your own system, you can first specify a type system in a textbook way, by which we mean you can just use techniques that you could find in the exercises for types in programming languages to specify a simple subtyping relationship that is easy to reason about and easily proven decidable. This simple subtyping relationship might not be able to recognize features like disjointness and distributivity, but there's where the second part of our framework comes in, which is you can specify extensions for subtyping that specify these additional relationships that you want. And our framework will then support you taking the parts that you prove and generate what we call integrated subtyping, which is a sound and complete decision procedure for your original simple system extended with your additional subtypings. So now I'll explain what each of these components are and how they work, starting with textbook subtyping. So first, in any language, you need a bunch of types. And in our framework, you will always have top and bottom, union types, intersection types. And then there's a set of what we call literals, which are the types that you fill in for your particular system. So if you have a functional programming language, this might be integers and function types. If you have an object-oriented language, this might be generic class types. If you have a structural language, this might be records and some base types. Once you have those types, you want to define subtyping. And in the first step, you define something we call declarative subtyping, where you just specify the properties that subtyping is supposed to have. And one important one is that subtyping should be transitive. So there's an explicit rule for that. Now you also want to be able to decide to have a decision algorithm for subtyping. And this transitivity rule is a problem there because it is not syntax directed. That is, you would have to come up to guess some middle type in order to be able to check whether this rule holds. And there is no good way to come up with such a type. So the standard approach to solve this is to come up with a separate set of rules, which we call reductive subtyping rules, that do not feature transitivity and rather have a similar set of all the other rules that are modified to bake in transitivity. Those rules are supposed to be syntax directed and well-founded to specify a subtyping algorithm. So for example, you might specify subtyping for functions as being contrariant in the argument type and covariant in the return type. But for reductive subtyping, you need to merge these two concepts into one rule in order to bake transitivity into the rule. And now you have to prove a few key properties about the system you specified. For example, that you can express the rules of each system in combinations of rules of the other to show that they're equivalent, and the reductive system actually expresses the specification for subtyping you had. Once you have proven those parts, our framework takes away some of the tedious work for you and proves all the standard parts about subtyping for units intersections. That's really the same for every system, and provides you with a decision procedure for your overall subtyping algorithm. Now, so far we have done nothing new. We have just formalized the standard way of proving subtyping for a system that you can do when following the textbook approach. But these standard rules do not capture all the subtyping relationships you need. One of them is distributivity, which we needed in our example in the beginning. So distributivity is this idea that the following equivalence holds, which is that intersections distribute over unions. And while our textbook subtyping relationship can prove one half of this equivalence, it cannot recognize the other one, and therefore the equivalence doesn't hold itself. But if we look at the left-hand sides of these subtypings, we see that the left-hand side of the subtyping that does work is in what we call disjunctive normal form. And on the other hand, we see that the left-hand side of the subtyping that doesn't work can be brought into this disjunctive normal form by applying an operation called DNF. And disjunctive normal form has this property that the DNF of a type is in disjunctive normal form. And furthermore, it has the property that if a type is in DNF, and we can prove in our system that it is a subtype of some other type B, then it is also a subtype of the disjunctive normal form of that other type B. We call this property promotion, and it is the key property that lets us prove transitivity in a system that is extended with reasoning about distributivity, provided that we can show that the left-hand side of a subtyping is in DNF. And this works really well for the standard rules for unions and intersections. So for example, here is the subtyping rule for left-hand side unions. If we assume that the union on the left-hand side is in DNF, then we automatically see that the left-hand sides of the premises that we have to check recursively are also still in DNF, which preserves our invariant. But this might not be true for the subtyping rules that you specify for your particular system. For example, here's the subtyping rule for functions. The left-hand side here in the conclusion is trivially in DNF because it's a function type and there are no intersections or unions to be distributed. But their components might not be. And those components are what end up in the left-hand sides of the premises we need to check recursively. So here B, for example, is not necessarily in DNF. And similar, the left-hand side of the other premise we need to check is coming from the right-hand side of the original conclusion, which we made no assumptions about in the first place. So you might think, okay, well, let's just bring everything into normal form everywhere as deeply as we can. But that doesn't work for systems like Ceylon, where you have inheritance that recursively expands types as you apply inheritance while you step through subtyping. So we do the other obvious thing, which is to apply the disjunctive normal form operator recursively in those steps in subtyping. But that breaks all the natural proofs of compositions that you might get from our promotion property earlier. And so while this change to the subtyping algorithm is really simple for you to do, there is a bunch of proof work that we needed to do in our framework to show that the resulting system is still well behaved. But we do that. So if you give us your specification for a simple textbook subtyping algorithm, we not only give you a decision procedure for the simple rules for unions and intersections with the ones for your system, but we even can give you a sound and complete algorithm to decide subtyping with unions and intersections that also recognizes distributivity. But distributivity, again, is not everything. And our framework, luckily, is more powerful than that, so we can solve more problems. And one of them is disjointness, which is the other property in our Ceylon example that we needed that is complicated to implement. Now, disjointness is a more domain-specific property of your system. Depending on your language, you might have different ones. And so our framework provides a way for you to specify subtyping extensions to capture these domain-specific problems in your language. In order to do that, you'll need to specify a few parts and proofs about them. The first one is you'll need to have an idea of what the additional subtyping relationships are that you're looking for. So in our example, null was disjoint from object. And in general, you might have an idea of certain types being disjoint from each other, and therefore having no common instances, and therefore their intersections being empty in the subtype of bottom. So in our example, we had this, the strings, the nullable strings intersected with object, and we brought them in DNF in disjunctive normal form to recognize distributivity. And that was enough to recognize distributivity, but it's not enough to recognize disjointness. So as a second step, you need to specify what it is that's missing in order to recognize disjointness with what we call an intersectedness predicate phi. And this intersectedness predicate phi works modularly on the lists of literals that are at the leaves of this tree of unions and intersections that the disjunctive normal form produces. So the reasoning for you is rather local in terms of the types that you build your system with. Now, string and object are fine. They have no problems with respect to disjointness. So phi holds for this part of the type. But when you look at null and object, those two types are disjoint. So phi doesn't hold. And now you'll need to provide us with an operation to bring this type into a better form to recognize disjointness. And this is something we call an intersector. The intersector is, again, an operation that depends on DNF. So it's combined with DNF to be applied to all of the intersections that DNF produces. And again, we apply it to this intersection of string and object, and that's fine. So the intersector leaves it alone. But null and object are disjoint. And so the intersector replaces it with bottom in the returning type, in the resulting type. And so the result of applying DNF with the intersector results in a type that is still in disjunctive normal form, and where all parts now satisfy this intersectedness predicate that you specify. Now that you have specified these parts, you need to prove a few key properties. And for that, let's remember what we did for disjunctive normal form. And we need to basically replicate this for extending disjunctive normal form with our intersectedness predicate and intersector. So if we apply DNF and the intersector to a type, it is necessary for you for us that the result is now in disjunctive normal form and satisfies the intersectedness predicate. And furthermore, we need to prove promotion, which is that if a type is in DNF and satisfies the intersectedness predicate everywhere, and we can prove that it is a subtype of some other type B, then we can prove that it is a subtype of that other type B with DNF and the intersector applied to that. That's a lot of stuff to prove, but the proof obligations for you are actually smaller. They are in terms of the components that you proved plus your literals. So that, for example, you need to just prove that the intersector applied to a number of literals is in disjunctive normal form with V. And our framework extends this for you to arbitrary types where DNF is applied globally. Once we have these properties, we can do the same trick as we did for disjunctive normal form, but instead of just the disjunctive normal form operator, we apply DNF plus the intersector in the recursive steps of your literal subtyping rules. This is an easy change for the algorithm, and all the proof work is basically done by our framework to combine your simple textbook subtyping relation with your extensions to get not only distributivity, but what we call integrated subtyping, which is a sound and complete decision procedure for your textbook subtyping, plus whatever extensions you wanted to specify. So you have these small extensions with proportional work to proof work to whatever you wanted to specify there. But you might do more of them. There might be multiple different subtyping features that you want to recognize, and it's nice to specify them separately. And the good news is that our framework is actually compositional. That is, there is a way for you to take two extensions and with a small proof about their compatibility, construct a bigger extension that encompasses both of them, and then give you integrated subtyping that recognizes textbook subtyping plus everything in both of these extensions. And the only thing you need to prove is the following thing. If a type is intersected by the standards of the first intersector, then applying the intersector of the second intersector needs to preserve this intersectedness property. That is all. Once you prove this, we can show you that we can construct all other parts and all other proofs about this new composition of intersectors automatically. And this is the key thing that lets us also let us model more Ceylon, more extensions of Ceylon individually. So, for example, Ceylon models abstract data types by enumerating the potential subclasses of a class. So, and you could see such an abstract data types really as a union of all its cases. Furthermore, since null and object are the only subtypes of top is really equivalent to the union. All values in the language are really instances of either null or object. And there is an extension called principal instantiations, which essentially lets intersections distribute over generic type arguments, which turns out to be very useful in generic type argument inference. All of these extensions can be specified and proven individually and then composed with our composability theorem. But our framework is not necessarily restricted to just Ceylon. We can also model extensions for other languages, like typical extensions that have come up in the literature for functional languages. So in summary, we provide a framework that is also provided as a Coq library for you to first define subtyping in a very simple textbook way that is easy to prove and formalize, and then provide extensions to capture additional subtyping relationships that might be hard to otherwise integrate into your subtyping relationship. And provide you with a sound and complete decision algorithm for these extended systems in a composable way. And I encourage you to go to our website and try to download the paper and look at the Coq framework to try it out yourself. Thank you.
Okay, we have time for a couple of questions. I'm going to start with one that came in on Slido from someone anonymous. And they ask, could the same kind of framework be used to reason about other kinds of structured types with equivalences, such as behavioral types?
Sorry.
Behavioral types.
Yeah, what was the start of the question?
The start of the question is, could you use the same kind of framework, or possibly exactly your framework, to reason about other kinds of structured types, such as behavioral types?
That depends on what we want to do. So we have some results on this actually being a more general principle, that you can kind of normalize types on the left-hand side and get additional subtyping relationships. There are a few restrictions to that we are still trying to figure out. There are a few properties of units and intersections that make them particularly nice to do, but we're confident that we can eventually extend this to more things.
Thank you. Do we have any local audience questions?
So thanks for the talk. This was really quite fascinating. What do we know about the time complexity of the decision algorithm that comes out of the framework?
So since bringing types into disjunctive normal form is exponential, there is basically, some exponentialness involved, but usually types are rather small. There are instances of type systems where this might not be true, in which case you might still be able to formalize it this way and try separately to find a more optimal algorithm and prove that equivalent to your thing separately. But the properties about your system still hold.
Hi, thanks. Yeah, nice talk. So it seems like one way to generalize your system further would be to include negation types and also recursive types as well. Could you comment on that?
So the question is, negation types, can you include negation types and recursive types? So recursive types, I mean, isorecursive types are certainly fine. They are not really a challenge. Equirecursive types are co-inductive, and you would need to do some more work to make the system extend to capture these kinds of things. Sorry, what was the other thing? Negation types. That seems, so one part, that seems to be about the difference between semantic subtyping and our approach. And for negation types, it seems that you would need a little more completeness in your system, which is a thing that semantic subtyping does really well. And our system doesn't really depend on your thing being complete. If you have one, I don't see why it would be a problem immediately, but I would have to think about that more.
Let's thank Fabian again.